Hello, in this video we'll be doing checkpoint 5.25. They want us to write the 5 different iterated integrals equal to this given integral. Alright, I think first what we need to do is to figure out what this region looks like. I can see that the region from the x values go from 0 to the square root of y. So if we can draw a function x is equal to the square root of y, that looks like in 3 dimensions it would look like a cylinder. By cylinder I mean it'll run along the z-axis, and if I graph x is equal to the square root of y in the xy plane, then my z-axis it'll be a cylinder, a surface going up along the z-axis. And then our y goes from 0 to some function, y is equal to 4 minus z, and then our z are constants. The outer limits are always constants. Okay, let's see if we can draw this out. Let's see if we can just imagine this whole thing on the xy plane. On the xy plane, I would get x is equal to 0, so that's this axis, and x is equal to the square root of y. So x going from 0 to the square root of y means it's going to go from 0, and then if we take a look at this, y is equal to x squared, that's the equivalent function, and that would be a parabola going up this way, or you can look at it as a square root function with x and y. Alright, so pretend that this is a cylinder. The cylinder goes up along the z-axis, and it was blocked off here. So this is what we have so far. It's probably going to get trimmed up a little bit because the y looks like it's going to go from 0 to some other function. So what we need to do here is we need to restrict our view to just look at the y z plane. After you do the first inner integral here, you're going to be left with a yz plane, and the y looks like it's going to go from 0 to 4 minus z. So what does y equal to 4 minus z look like? If you want to switch this around, this is equivalent to saying z is equal to 4 minus y, and or you can say y plus z is equal to 4, and that's just going to be a line with a slope -1. It goes from -4 or 4 in the x-axis, or 4 in the y-axis, and 4 in the z-axis. Alright, now we want to recreate that drawing. I'm going to draw this in a different color. And by the way, z goes from 0 to 4, so it's going to go from 0 to 4. So if we recreate that drawing, we want to recreate that drawing here on the 3-dimensional space. So if we mark this at 4, that's this 4 over here, and then we look for the 4 in the y as well, that's this 4 over here, and draw this line going down. That's that line. So this is the back of the surface that we're looking at, and so I think then we're seeing the surface get cut a little bit, and if we cut this at 4 right here and have it go up, maybe we can do this in another color. Looks like it'll curve a little bit. Okay. That means we're also looking at this. This is a graph in 2 dimensions, y, z, but we can also look at this as a surface. And so that surface would actually be a plane that has its domain restricted. So the plane is z is equal to y minus 4. And if we were to graph that, we'll see that's a slanted plane. Another cylinder, we would call it, but it's actually a plane. Okay? All right, well, the first set, according to this integral, the first set of limits look like this. So the outer limit goes from 0 to 4. The intermediate limit goes from 0 to y goes from 0 to 4 minus z, and then the inner limits go from 0 to square root of y. All right. We can stick with this to get our second set of integrals. We can keep this as a function of x first, and then change the limits to go, instead of going along the y-axis, going from 0 to this function, we can go along the z-axis first. So our second set of limits could be the same for x going from 0 to square root of y, and then we'll change the z and the y. So z goes from 0 to 4 minus y, and y, constants, these are the last limits, goes from 0 to 4. So we essentially kept the same x limits, except we switched the way we saw the two-dimensional, whatever's left in the 2 dimensions. So then our integral here would look like triple integral. The inner integral is still x going from 0 to square root of y. This is your function. And we're going to integrate with respect to x first. And then instead of y, we're going to go z from 0 to 4 minus y. And then our y limits are last, constants going from 0 to 4. Okay, so finding that was fairly easy because we kept the same inner integral, and so we really just fiddled around with the two-dimensional version that's left. All right, now let's integrate differently and see if we can recreate this drawing here. Or instead of recreating the drawing, I will just copy and paste that drawing. And then let's see if we can approach it from a different set of limits. We integrated with respect to x first. Let's now do our integration with respect to y first. So integrating with respect to y, you would draw a line parallel to the y-axis. This is the y-axis. Oh, maybe we should do z first. Let's do a line parallel to the z-axis. And we're going to enter the region when z is equal to 0. And then we're going to be in the region and then get out of the region on this plane that we had talked about. That's the plane z is equal to 4 minus y, and then you can also see that backwards. All right, once we have that, we can focus on the two-dimensional shadow that's left, and we integrate with respect to z, and now let's integrate with respect to x and y. So our x and y look like this. We had a y, x is equal to square root of y, and then we saw that that's essentially saying y is equal to x squared. So those two are the same. And now, if we decide we're going to integrate with respect to y first, we would draw a line parallel to the y-axis, and we would enter through the region when y is equal to x squared, and then we're going to exit the region when y is equal to 4. And then we didn't really check on this, but this is going to be the intersection between y is equal to 4 and x is equal to y squared, so that's x is equal to 2. So your x limits are going to go from 0 to 2. So there is our third version of the integral. The inner integral goes from 0 to 4 minus y. You have your integrand. The inner integral is going to be with respect to z, and then we're going to go with respect to y, going from x squared to 4, and then with respect to x going from 0 to 2. Alright, now similar to this and not so difficult is that we keep the z going from 0 to 4 minus y squared. And now let's change our viewpoint. Instead of integrating with respect to y first, let's integrate with respect to x first. We would draw a line parallel to the x-axis. We would enter through this point x is equal to 0 and exit through this point x is equal to the square root of y. And then your y goes from 0 to 4, the constants. Okay, so that makes our another set of integrals. Again, the inner integral is going to be the same, going from 0 to 4 minus y squared. You have your integrand, and you're integrating with respect to z first. And then with respect to x, you're going to go from 0 to square root of y. And then with respect to y, you're going to go from 0 to 4, constants. Okay. So that's the second set. We had 2 from the first set, including the first one. We had 2 from the second set. Now let's figure out if we integrate, decide we integrate with respect to y first, how that's going to look like. I just recopied this function again, or this surface that we're looking at, or the region, and now we are deciding to integrate with respect to y first. If we integrate with respect to y first, we would draw a line parallel to the y-axis, and we would enter through the region through this surface. Now this is that surface, remember, this is surface x is equal to the square root of y. It's a three-dimensional surface, remember, that's a cylinder. So if we integrate this with respect to y first, then your y is going to be equal to x squared. So let's integrate with respect to y first, and we're going to go from this surface itself, y is equal to x squared, and then we're going to be in the region, and then we're going to get out of this region through this plane. This plane is I think we labeled it already here. It's z is equal to 4 minus y, or y is equal to 4 minus z. So that's going to be your top limit, 4 minus z. Okay. Now the tricky part about this scenario is to see the shadow on the xz plane. And the shadow on the xz plane is a little tricky to see, but you can see that this should be part of the shadow, and then it looks like it kind of curves. Now I don't know exactly how the curve is going to look like, if it's going to look like this or if it's going to look like this, but it's going to be the shadow that it's going to make on the xy plane. And what we're doing is we're pretending, when we talk about drawing a line parallel to the y-axis, it would be hitting this, it would be going through this plane, and then it's going to hit this surface and then get out of that surface. So that's how we were able to identify the two surfaces with respect to y. but the shadow is what we want to see. And we can find that shadow on the YZ plane if we take maybe this function. We know that there's a relationship here between x and y, and we know there's a relationship here between y and z. So if we get y by itself here, and we get y by itself here, and set them equal to each other, let's see what we come up with. So we'll set those equal to each other, and remember, we're trying to figure out what's happening on the xz plane, and we set them equal to each other. We're going to get x squared is equal to 4 minus z. And if we solve for this, this is going to be, I think it would be better if we brought the z over to the other side, and 4 minus x squared. This is going to be an upside down parabola that's shifted up 4 units. So this is 4 units, upside down parabola. And of course, we're really just concerned about the positive side. So this must be the region that we're looking at here. And that's the region that we're going to deal with in 2 dimensions. All right. So now that we have that, we can say if we integrate with respect to y first, and then we can decide if we integrate with respect to x or z first. Let's say we're going to integrate with respect to z first. We'll draw a line parallel to the z-axis, and we would enter through the region when z is equal to 0, and we're going to exit through the region when z is equal to this function. Z is equal to 4 minus x squared. And then your x limits, constants, go from 0 to 2. All right, now we have our 5th integral, the 4th one that we're looking for. And this is going to say we're going to integrate f of x, y, z with respect to y first. And the y limits go from x squared to 4 minus z. And then we'll integrate with respect to z next, going from 0 to 4 minus x squared, and then finally integrating with respect to x, going from 0 to 2. Okay. And then we have one more integral to go, and with this integral we're going to keep the innermost integral, limits of integration, that's the y, going from x squared to 4 minus z. And then we'll decide this time to integrate with respect to x first. And we focus on the 2-dimensional picture. Integrate with respect to x first. You would draw a line parallel to the x-axis, hit 0, and then hit x is equal to whatever this function is. And for this, we'll take x squared is equal to 4 minus z and take the square root of that, and ignore the negative because the negative's on this side. We don't need that. We just need the positive part, and that's going to be your upper limit. And then constant limits, 0 to 4 for y. And then that's it. We'll write this integral as the integral of f of x, y, z, first with respect to y, going from x squared to 4 minus z, and then with respect to x second, from 0 to the square root of 4 minus z, and then with respect to z, oops, this should be a z, sorry. Z limits go from 0 to 4. And there you have it. I tried to recreate this plot using CalcPlot 3D. And if we take a quick look at this, this particular CalcPlot 3D graph has a region, a 3-dimensional region, and then I also drew the 2-dimensional plates, shadows that it makes. The region itself is the last plot. So you can go to the last plot and uncheck that to hide the plot. And these are the shadows that they make on the XY plane, the YZ plane, and the XZ plane. So for example, the original integral had an integral with respect to x first and then y and z. And then if we take a look at the YZ shadow and then draw the region right next to it, you can see that the YZ shadow is that shadow that it makes on the YZ plane. Now if we want to take a look at what happens on the XY plane, what we want to see is the shadow that this makes on the XY plane. So if we want to uncheck the region, you see the shadow that it makes on the XY plane. We'll recheck and uncheck, and you can see it disappear and reappear and see that that is in fact the shadow. And then finally, the more difficult one, because it's not up against the XZ plane, the shadow that this makes on the XZ plane is this upside down parabola that we saw. If we look at it directly along the Y, you see the XZ plane over here. So one thing we can do is we can make that region disappear again, see just the shadow part. And then you can look at this from different points of view, so you can see how the region itself looks like and how the shadows look like on the remaining two variables after you have integrated with respect to one of them. Okay. All right. So this was a lengthy one, but I hope you can see the different points of views of the region and how the region works when you're doing a triple integral. Once you integrate with respect to one variable, the other two variables are going to be the regions left to integrate, and so it'll be like looking at a double integral. Whew. I hope that helps.